Okay, in this video we'll be discussing MCQs of the chem bonding tutorial. So question 14, we have a question on shape and bond angle. So we have this molecule alanine. So we are supposed to discuss the various bond angles X, Y, and Z for the compound. So if you take a look at the carbon highlighted in yellow, okay, to determine the bond angle, we can first count the number of bond pairs and lone pairs. So on this carbon, you can see there's 3 bond pairs and 0 lone pairs. Okay, because you can see that the carbon clearly form 4 bonds, 1 bond, 2 bond, 3 bond, 4 bonds. Alright, a quick recall, your double bonds and single bonds are also considered as a 1 bond pair. So in this case, the shape around this carbon will be trigonal, planar, based on VSEPR theory, and therefore 120 degrees. Alright, for the carbon that's highlighted in green, the angle Z, you can see clearly 4 bonds, 1, 2, 3, 4. Right, 1, 2, 3, 4. So it's a case of 4 bond pairs, 0 lone pairs. The shape will therefore be tetrahedral, and the bond angle will be 109.5 degrees. Okay, for the last atom, sulfur, in the remaining central atom, you have 1 bond pair, 2 bond pair, 3 bond pairs. So 3 bond pairs and 1 lone pair. So this will give you a trigonal pyramidal shape. Okay, so how do I remember the shape so fast? Remember, when we were going through this, we said that it's important to consider the total number of electron pairs. So 3 and 1 total, you have 4. You start with tetrahedral. You remove one of the bond pairs and replace it with a lone pair. You get a shape that has a triangular base, so that's trigonal pyramidal. The bond angle from origin tetrahedral of 109.5 will decrease to 107 degrees. Okay, and as a result, which of the option to the nearest 10 degrees will fulfill this option? It will be option A. Okay, so over here, it's important for you to take note that you don't be overly simplistic and look at this X as a 180 bond angle. Okay, so do not be fooled by such display. Alright, do not think that Y and Z will also be 90 degrees. Alright, do remember to use your VSEPR by counting number of bond pairs as well as lone pairs to determine the shape and subsequently the bond angle. Okay, so as I've mentioned, a quick summary. So look at number of lone pairs and bond pairs around the central atom, determine the shape and therefore the corresponding bond angle. So it's similar to what I've explained earlier on, and that's why the answer will be A. Okay, moving on. Okay, 15. Which molecule has the largest dipole? So in A itself, you can see that A only has carbon and hydrogen. They have very similar electronegativity. And as a result, in this case, there won't be any dipole moment. Alright, because there's no delta plus, delta minus. C and H has very similar electronegativity value. Okay, whereas in B, the carbon-oxygen bond will have a delta minus and delta plus because oxygen is more electronegative than your carbon. And as a result, you have a dipole moment along the CO bond. And this translates to a net dipole moment that's pointing towards the oxygen. So in this case, you do have a dipole moment. Alright. For the case of C, you have now chlorine atoms in addition to your oxygen atom. So all the bonds here are actually polar. So you have delta minus, delta minus, delta minus because your chlorine is more electronegative than your carbon. Oxygen is also more electronegative than carbon. So you have a delta plus carbon. Alright. In this case, there will be 3 bond dipoles. Okay. But it's worth noting that the dipole moments along the CO bond is larger. Right. So this is larger. Why? Because O is more electronegative than chlorine. So as a result, the difference in the electronegativity between carbon and oxygen will be a lot larger as compared to the electronegativity difference between chlorine and carbon. So this vector here, if you look at just vectors, this vector here will be of a larger magnitude. Alright, so when I resolve these 3 vectors, because of the two vectors pointing along the CL, it will sort of negate partially the dipole moment of this, and that's why you can see the net dipole moment will be somewhat smaller than compared to B, where B doesn't have any chlorine to pull in the opposite direction. Okay, last but not least, in D, you have a CCl bond, which is the polar bond. So same thing, you have a delta plus, delta minus. Right, so I'm drawing out the dipole moments as well as the dipoles. You can see that these two dipoles that I've highlighted in yellow are directly opposite each other. Alright, it's facing in the direct opposite direction, and that's why it will cancel out, and therefore there's no net dipole. Okay, so in this case, A and B are non-polar molecules. B and C are polar molecules, but in this case, which one has the largest dipole? B will be the one with the largest dipole. Okay, moving on, we go on to 16, where we look at ice. So to illustrate this diagram better, what I've done is I've highlighted separately all the water molecules. Alright, the dotted lines that you see are basically your hydrogen bonds. Okay, so recall your hydrogen bonds are formed between your delta plus hydrogen that's bonded to F, O, and N, as well as the lone pair of electrons on F, O, and N. Okay, so all the bond angles surrounding each oxygen atom will be 120. So let's focus on this particular oxygen here. You have one bond pair, two bond pair. Alright, and then you also have two lone pairs around your oxygen. Alright, that's involved in the hydrogen bonding. Alright, so these two lone pairs on the oxygen atoms are involved in hydrogen bonding. So there are 4 bond pairs and 0 lone pairs around each oxygen atom. If I view it, that this hydrogen bond is formed. Alright, so the lone pairs are also used in bonding, in hydrogen bonding. So each O atom will have 4 bond pairs and 0 lone pairs. Each O atom is actually tetrahedral, and you have this 109.5 degrees. Okay, so and this, because of this tetrahedral structure and this bond angle, this result in ice having an open cage-like structure. Okay, so you can see there's pockets of space within your ice, and this leads to ice having a larger volume. So this is a common phenomenon that we see when we freeze water. For example, in the plastic bottle, you will see the plastic bottle becoming bloated. Alright, so ice expands upon freezing. Alright, so there's a larger volume because of this open cage-like structure in terms of how the oxygen orientate itself to form in a tetrahedral fashion. Okay, so how many electrons are involved in from each oxygen involved in hydrogen bond? So you can clearly see from the diagram I've annotated earlier on. Alright, so let's focus back on this central oxygen. So this oxygen here, you can see the two lone pairs on the oxygen are involved in hydrogen bonds. So each oxygen atom consists of lone pair of electrons, 2, to form a hydrogen bond. So each H2O molecule forms 2 hydrogen bonds, and therefore 4 electrons are involved. So B will be a correct option. This one is wrong because it's 109.5. Okay, then before we go on to conclude this, let's check through C and D. So in this case, B is a correct option, and therefore C and D must be wrong. So the hydrogen bonds shown by the dotted lines are stronger than OH covalent bond. That is definitely wrong because hydrogen bonds are intermolecular forces of attraction, and these are weaker than covalent bonds. Last but not least, the open structure of ice causes ice to be denser than water. That's not true. So open structure of ice result in the volume increasing, then this makes ice less dense than water, and therefore ice float on water. And that's what we see typically in glaciers, right? So your icebergs typically float on water, and therefore the answer will be B. Alright, the only correct option. Okay, moving on. Okay, we have question 17. Which of the following substances contain at least 2 types of bonds or forces of attraction? So we take a look at neon. So neon, it's a noble gas. So it's monoatomic. So you have neon atoms, and because it's only monoatomic and it's simple molecular structure, the type of interaction between your noble gas will be typically your ID. So neon only has weak ID between neon atoms. Alright, there's only one type. So option 1 will not be a possible answer. For ammonium chloride. So ammonium chloride, you have NH4 plus Cl minus. Between the NH4 plus and the Cl minus, you have your ionic bonds. Okay, so you have ionic bonds between opposite charge NH4 plus and Cl minus ion. This is one type of bond. But within NH4 plus, alright, so if I draw the dot and cross for NH4 plus, you have N with 5 valence electrons. So 1, you form a single bond with 1 H. You form a single bond with another H. Third one, you form a third single bond with another H. And you still do have a lone pair. And now because it's NH4 plus, one of the H will not be having any electrons. And that's why you see a dative bond forming over here, right, between the N and the H. So remember, the plus charge, you have to remove an electron, and you remove from the hydrogen, because hydrogen is less electronegative. When we remove electrons, we remove from the less electronegative element. So in this case, you can see that these bonds, what are these bonds? They involve sharing of electrons, right? And therefore, these are your covalent bonds. Okay, so typically when you see polyatomic anion or cation, they typically involve covalent bonds within the anion or cation itself. Example would be like SO42 minus, NO3 minus. If you draw a dot and cross for these two compounds, they also have covalent bonds within the anion itself, but you have ionic bonds between the cations and anions. Alright, so that's why there's two types of bonding. For graphite, this is a very classic example that you have learned from O levels. You have covalent bonds between your carbon atoms within a single layer. So within a single layer of graphite, your carbon atoms are joined together by strong covalent bonds. But between layers, you have what we known as your weak IMF, weak ID. So again, similarly, you have two different types of interaction, and that's why 2 and 3 are possible options. And that's why, in this case, the answer will be D, 2 and 3 only. Okay, moving on to our last explanation on boiling point of ammonia, carbon dioxide, and hydrogen chloride. This is somewhat similar to your check 4. Alright, so if you look at ammonia, when you're faced with such a question, typically the quick way that I'll ask you guys to annotate will be to look at the boiling point, which will be the highest. This is actually the lowest. This is the highest. Okay, the second thing that I want you guys to consider is to consider computing the MR. And last but not least, okay, consider what is the predominant IMF. Okay, so for MR for ammonia, it will be 3 plus 14, 17.0. Carbon dioxide will be 44.0. So all of this you can do it quite easily, 36.5. Okay, so you do see that the MR of carbon dioxide is the largest, but it has the lowest boiling point. Right? So in this case, the size of electron cloud is not the main reason to explain for the trend in boiling point. So it's worthwhile to consider the IMF. Ammonia, because you have N directly bonded, or rather H directly bonded to N, which is an electronegative element. Right? So you do have lone pair on N, and therefore you can have hydrogen bond for ammonia. For CO2, carbon is central atom. You form a double bond with oxygen. Alright, so you have a 2 bond pairs, 0 lone pair structure. It's linear. The dipole moments of carbon dioxide can be cancelled out. So it's non-polar, and therefore the type of IMF will be ID. HCl will be quite simple to draw. Both of them require a single bond to achieve a stable noble gas configuration. You have delta plus, delta minus, a net dipole that goes towards Cl. So you have a polar molecule. You have your PD. Okay, so if you take a look at the options, which of the following statements are correct? Ammonia has a higher boiling point than HCl because the hydrogen bonding in ammonia is stronger than the PDPD in HCl. Is that possible? Yes, true. Alright. The hydrogen bonds are indeed stronger than the PDPD, and it's reflected from the boiling point. Okay, moving on, CO2 has a higher boiling point than HCl because the PDPD in CO2 are stronger than the PDPD in HCl. So it's incorrect. Why? Because CO2 does not have any permanent dipole. Alright. So CO2 is non-polar, as I explained earlier on. Alright, so CO2 is non-polar, so it only has your ID. Okay, the reason why CO2 has a larger boiling point than your hydrogen chloride is largely due to its larger size of electron cloud. Alright, which leads to more extensive ID. Okay, moving on, part 3, the strength of the PD-PD interactions increases in the order HCl, CO2, and then NH3. Again, do you think this is correct? Does CO2 have any PD-PD? Alright, so CO2 doesn't have any PD-PD, so it only has ID, therefore this statement will not make any sense with CO2 in the middle. So CO2, it only has ID, does not have any PD-PD, so it's not correct for this statement. So out of the options, only statement 1 is correct, and therefore you will choose your answer to be A. Okay, with that we are done with the MCQs for this tutorial.